Okay. So when I was learning math, I wasn't really taught the foundations or the derivation of a lot of formulas. Like I was forced to accept the definition of the derivative or maybe the addition trigonometric formulas that we will be discussing in here. And as I grew older, I started to really like finding out the derivation of such. So in today's video, I'm going to derive the identities of sine A plus B and cosine A plus B. And I'm not going to put it yet. We will see as we go on the derivation process. Firstly, let's put out the basics. Sine and cosine, what are those? So let's have a right triangle in here. This is a right angle. So that is a right triangle. And this is some angle theta. Okay. Let's name the sides A, B, and C. Okay, sine theta is the opposite over the hypotenuse. So that's A over C. And cosine theta is the adjacent over the hypotenuse. So B over C. So if you remember SOHCAHTOA, that is it. And if we want to go one step further, tangent theta is A over B. That's why sine theta over cosine theta could be equal tangent theta. Because if you did that operation, you would get A over B. So, uh, there's another part in here. There's another angle that doesn't get discussed as often, which is 90 minus theta. How do I know this is 90 minus theta? Well, the sum of the angles in a triangle is 180. We already know that one angle is 90 and one of the other angles is theta. So the remaining angle should be this. So it's going to be remaining angle, which is going to be 90 minus theta. So that is the missing, that is the often forgotten angle. Um, what happens if we take the sine, cosine, and tangent of this forgotten angle instead of the other ones? So let's take sine of 90 minus theta. So that's still the opposite over the hypotenuse. This time the opposite is different. It's b now. So b over c. And for cosine of 90 minus theta, that's going to be adjacent to 90 minus theta is a over c, which is the hypotenuse. So actually, b over c, we've seen earlier, is cosine theta. And for cosine 90 minus theta is sine theta. So when we say cosine, it's cosine, right? So the co means complementary actually. So what this means is that the complement, if you take the sine of the complement angle, you have that's cosine. So cosine is just short for complementary sine, right? Hmm. So that's the first part. We're going to be using that fact later. A little bit before we go there. Mm, do you guys remember the Pythagorean identities? If not, I'll refresh you on that. So, oh, let me draw a triangle. Very nice. So this triangle, let's have data here. Then let's label this AB, but instead of C, let's set this to 1. This means A squared plus B squared is equals to 1, right? According to the Pythagorean theorem. Now, what is sine theta? Sine theta is A over 1, which is just A. Cosine theta, yeah, is B over 1 or just B. And we can substitute A and B here. We get sine squared theta plus cosine squared theta equals 1. That's the first that's the first Pythagorean trigonometric identity, right? And there's more. This let's label this A and C. Instead of B, let's label this as 1, such that A squared plus 1 equals C squared, or C squared minus A squared equals 1. All right. So, so sine theta is A over C. Does that help? I don't know. Maybe it will help later. Cosine theta, what's that? That is 1 over C. And then tangent theta is A over 1. So, or just A. we have 1 over c here. To make this to isolate c, we just multiply both sides by c and divide both sides by cosine theta. We get c equals 1 over cosine theta, or c equals secant theta. And we can substitute c here and a here. We get secant squared theta minus tangent squared theta equals 1. That's the second Pythagorean identity. And how do we find the third one? That's obvious. We just replace one of these with a 1. And b here and c here. And let's do the same rodeo again. Sine theta is 1 over c. And then cosine theta is b over c. And tangent theta is 1 over b. Sine theta is 1 over c. C is cosecant theta. Then b here is cotangent theta, right? 1 over tangent we know is cotangent, right? That's one of the identities. Now, let's go back here. So 1 squared plus b squared equals c squared. Subtracting b squared on both sides, we get c squared minus b squared equals 1. C squared is cosecant squared. C squared becomes cosecant squared. B squared becomes cotangent squared, and that equals 1. And that is the third Pythagorean trigonometric identity. Why did I show this? It's because this is the satisfying derivation that we can get if we think if we think uh, deeply enough in these kinds of fields. So this is the derivation that I wasn't afforded when I was younger, right? And this is a big frustration I have with some of the things that I am studying right now, is that there are no derivations, or we don't have time to discuss the derivation of something. Yes, I get that some of it's really long and rooted into deep mathematics, but most of the time they're just that simple. And it is so satisfying seeing all of this come together. So, with that out of the way, let's try solving for the addition identities. Now, we need a square. Before we do anything, we need to imagine what a plus b might mean. So, sine of a plus b, sine a plus b, it might look something like that. So, this is a, this is b, and then the total would look something like that. That would be that looks like a really hard, shape to get around. So let me draw it another way. So uh, something like that, and maybe like that. All right. So let's draw A like this. B. Oh. So this is angle A. We know this is a right angle. We can set this as a right angle. And let's try B on its own without do this. This angle sounds nasty. It looks nasty. So what I'm going to do is to make a right angle right there. Like that doesn't look right, but you know, you gotta contend with what you have. And then let's make a ceiling right there. So it goes like that. There you go. And then let's complete this. And what does that look like? That looks like a rectangle. Let's say this is a square. All right. This entire thing, entire construction, let's say it's a square. It doesn't affect, does it affect our calculations? Maybe. But let's just say it's a square. Oh, we all know it's a rectangle because, all that. But let's say it's a square. So this is A, this is B. These are our givens. How do we calculate anything else? What is this angle? We know this is 90 minus A, right? Because of the complementary angles. And this is 90 minus B. What is this then? We've established that this angle is 90 degrees. So this is 90 minus A minus B. This then is A plus B, right? Because 90 minus A minus B plus A plus B plus 90 is 180, which is the total angles, right? How about this one? So 180 minus 90 minus B minus A plus B. What is that? So 100 minus 90 is 90. Then minus minus B is plus B minus A minus B. That's going to be 90 minus A. So this is 90 minus A. And this should be A, right? And does it check out? Let's add A, 90 minus A, and 90 degrees together. And we get, oh, 180. So this figure checks out from all angles. So now that is established, let's name a lot of, let's name these shapes again. Let me move it right down here. There you go. Let's name some of them. So this is A, B, C. All right. We name this D. I usually skip E because I reserve E for Euler's number. So I go F, and then there's G, H, and then I skip I because that's the imaginary number. So I just go to J and K. It's very weird of me, but I do that all the time. So let's start with sine A. So sine A over C. What's cosine A? B over C. All right. For everything else, we can go just we just need sine and cosine. So what about sine of B? Well, that's going to be D over F. What's cosine of B? Well, that's going to be uh, cosine of B is C over F. And now, the thing we're trying to find is sine of A plus B and cosine of A plus B. So start with sine. Sine of A plus B, we want the opposite, K, over F, which is the hypotenuse. For cosine, we get J over F. So this is a lot to unpack, but we have our set of algebraic stuff. This is just algebra from here on out. So this is going to be easy. So first, the sine thing. All right. So sine of A plus B equals K over F. We have F, like we reference F here and here. K though, what do we know about K? Looking at this image, we can already see that K is A plus G. How do we know that? This is a rectangle at most, or a square, as I've explained earlier. It could be a rectangle or a square. It looks like a square, But let's assume it's a rectangle. This means that this and that are not only parallel but equal, since it's 90 degrees on all sides, and that fits a rectangle, right? Any rectangle has 90 degrees on all sides, even a square. So K is A plus G. Not only are they parallel, they're equal in size. So K equals A plus G. So we can put A plus G right here. All right. What else? What can we say? We don't have G for now. We have A, we have F, but G. Where do we find G? Ah, look at this. There's G in here, and then there's A in here. We can say that the sine of A, this is sine of A, is G over D as well. No, cosine of A, sorry. No, cosine, since it is adjacent side. So cosine of A is also G over D. So that's one possibility. There's G already in there. What else? Uh, do we have A over F? Where can we find the F? Of course, it's D over F, sine B, and whatnot. Look. So we have G over F, right? We have G over D and D over F. If we cancel D, we get G over F, which is one half of what we need. So that's good, right? So let's have G over F as G over D, D over F, and A over F. How about that? We have A over C and C over F. A over C times C over F. Cancel the C's, we get A over F. So we have A over F there. So A over C times C over F plus G over D times D over F. Now, after this, we just put in the trigonometric equivalence. So sine of A plus B is A over C, sine A, C over F, cosine B, plus G over D, which is cosine A, D over F, which is sine of B. And there we go. That is the addition identity of sine. That's easy, right? So that feels really good. How about cosine? Can we do the same things with cosine? Oh, let me just move this one down here. Okay, J. What is J in here? Hmm. J doesn't look like it equals anything, but B and J and H, I think they have something similar. So B equals J plus H, right? Because B and J plus H are parallel and in equal in size because it's a rectangle. So we can say B equals a J plus H. And since we just need J, we can go B minus H on top over F. So this B minus H because algebraically you just subtract H from both sides, right? Like that. So B minus H over F. Do we have B over F? B over F. Look. There is cosine A, cosine B. There's B over C and C over F, right? B over C, C over F. We can do this as cosine A, cosine B. So B over F is B over C, C over F minus H over F. Where is H? This is H. So sine A is H over D. Aha. So if this is H over D and D over F, we can cancel the D's and we get H over F. So H over F is H over D, D over F. This is like a scavenger hunt, right? So it's really exciting how you can how you can derive all this. So B over C, that is cosine A. C over F, that is cosine B. H over D, that's sine of A. And D over F, that's sine of B. And there you go. That is the addition identities for cosine, right? And yeah. So what else can we do from here? What if A and B are the same thing? So what if A and B are equal to something like X? So like sine of X plus X. What is X plus X? 2X, right? So we can get the double angle identity from here. So we just apply this sine A cosine B plus cosine A sine B, and put X where A and B are. So this is sine X cosine X plus cosine X sine X, or 2 sine X cosine X. That is the double angle identity, right? And cosine of A plus B, or X plus X, this is going to be the double angle identity for cosine. So what is it? Cosine X minus sine X sine X. So that is cosine squared X minus sine squared X. Nice. After that, what else? Well, cosine squared, this invokes something that we discussed earlier, right? Sine squared X plus cosine squared X. So can we do anything with that? Let's take this. Put it right here, right? What if I added this? sine squared x. Mm, sine squared x. But I need to subtract sine squared x again. Why do I need to do this? Sine squared x minus sine squared x is 0. So in a sense, in essence, we're adding 0 here. So we're not actually changing anything about the original equation, right? So cosine squared plus sine squared, that becomes 1. The negative sine squared minus sine squared, that's 2 sine, negative 2 sine squared x. And that's one of them, right? If instead we did this, instead of sine, we got cosine. Uh, and let's reverse the signs for now. Yeah, that's actually fine. So negative sine squared x minus cosine squared x. That's negative 1. And cosine squared x plus cosine squared x is 2 cosine squared x. So that's another part of the double angle identity for cosine. So we're doing a lot of things here, right? What else? So this is cosine 2x. From here we can extract we can isolate sine squared and cosine squared, right? So from one side, sine squared x, let's just skip the algebra for now. This is 1 minus cosine 2x over 2, right? Uh, and the other one, cosine squared x, is 1 plus cosine 2x over 2. So from squared, we've uh, from sine squared x, we can therefore conclude that it is equal to this, right? So that's pretty good. And this is the kind of things that I wish I would have known 5 years ago. So, so for some of you who are starting their mathematical journey, please learn about the derivation of stuff. Please be curious about how stuff is derived. So there's a lot of things that can be derived that can be taught to you by step. But most teachers elect to skip all that because we don't have time. And I understand that. We really don't have enough time to teach. And maybe that's the fault of the system, not the students or the teachers, but it's still good to know how things are derived. So in my free time, I usually just find stuff to derive and find. All right, there's one more thing before I go. Tangent identity. So sine sine A cosine as sine A plus B over cosine A plus B. That's going to be tangent of A plus B. So the sine identity is sine A cosine B plus cosine A sine B over cosine A cosine B minus sine A sine B. From here, we can multiply and divide both sides. So on the top here, it looks like we can divide cosine A cosine B. We also do that on the bottom. What happens here? Cosine B in here gets cancelled, so sine A over cosine A is remains, so that becomes tangent A. Similarly here, tangent B remains. Over cosine A cosine B becomes 1 minus sine A sine B over cosine A cosine B, that's tangent A tangent B. If it is the double angle identity for tangent, then A and B becomes x. So top becomes tan x plus tan x, which is 2 tan x over at the bottom, which is 1 minus tangent squared x. There you go. And yeah, this is just a couple of the derivations I really want to expound right now. And I hope you enjoyed. I hope you find something interesting today, even if you know it. Maybe I've showed you some tips on how to really enjoy math. This derivation is how I enjoyed math from the day stopped learning math as a school project and more like a hobby. And I'm still learning it, but not in the capacity before, right? So yeah, thanks for watching, and I hope you have a great night.